Welcome back, students. So we'll continue with the Thermal Physics 1 course. And we covered a great deal of information about heat transfer mechanism. And the part which was left out was radiation. So I'll try to cover some of that. And then we'll start a new part, which is the heat conduction equations. Now, as you understand, this course has several parts. So my colleagues are actually covering the initial, the basic concept about kinetic theory, transportation phenomena, and Brownian motions and its applications, real gases, conduction of heat. So like real gases and all that, whereas the conduction of heat and radiation and all this part I'll be covering here. So part of which we have covered in lecture 1, which is thermal conductivity, diffusivity. We have some idea about what it is. So we can go into further advanced topics like Fourier equation for heat conduction. And we can try to solve some of these equations for real life scenarios. Then we'll further go into radiation as a full scale chapter, but I'll just give you some introduction here. Now, getting back to radiation. So what we're dealing here is more the heat transfer by radiation. It's basically the energy emitted by matter in the form of electromagnetic waves or photons as a result of changes in the electronic configurations of the atoms or molecules. Unlike conduction and convection, the transfer of heat by radiation does not require the presence of intervening medium. So the difference between other methods is clearly the intervening medium. So this time we don't need any medium because photon can, it's electromagnetic radiation, so it can travel across vacuum also. In fact, heat transfer by radiation is fastest at the speed of light because it's electromagnetic wave, and it suffers no attenuation in vacuum. This is also the energy of the sun, the way that energy reaches sun with this method only. In heat transfer studies, we are interested in thermal radiation, which is the form of the radiation emitted by the bodies because of their temperature. All bodies at a temperature above absolute zero emit thermal radiation. Radiation is a volumetric phenomenon, and all solids, liquids, and gases emit, absorb, transmit radiation to varying degrees. However, the radiation usually considered to be a surface phenomena for solids. So radiation is basically governed by this law, which is the Stefan-Boltzmann law, in which the amount of energy or the quantity of heat is actually transferred can be calculated in terms of this. We'll just get to that in a minute. We have to understand the factor, which is Stefan-Boltzmann constant, and also the idea about black body radiation. We'll understand more of these things as we progress, and we'll cover a great deal about information about the radiation and all these formulas. It's just for your introduction. That is the, so black body is basically, it's idealized surface that emits radiation at the maximum rate. So emissivity is also defined here. which is the measure of how closely a surface approximates a black body for which the emissivity is 1 of the surface. So some of the materials emissivity will actually written here. The black body radiation represents the maximum amount of radiation that can be emitted from a surface at a specific temperature. The absorptivity is the fraction of the radiation energy incident on a surface that is absorbed by the surface. A black body absorbs the entire radiation incident on it. So the Kirchhoff law is given by that the emissivity and the absorptivity of a surface at a given temperature and wavelength are equal. The absorption of radiation incident on an opaque surface of absorptivity can be given by some simple rules. Now, when we have to deal with net radiation heat transfers, the difference between the rates of radiation emitted by the surface of the radiation absorbed, we can actually deal with this method. It's complicated in terms that when we have to determine the net rate of heat transfer by radiation between two surfaces, we have to consider the properties of the surfaces, the orientation relative to each other, the interaction of the medium between the surfaces of radiation. So the radiation is usually significant relative to conduction or natural convection, but negligible relative to forced convection. So when we're dealing with net radiation of heat transfer, when a surface is completely enclosed by a much larger or black surface at temperature, the surrounding separated by gas, such as air, that does not intervene the radiation, the net rate of radiation can be given by this. So that's the energy transferred, the heat transferred between two surfaces. When radiation and convection occur simultaneously, we can actually have a combined equation like this, whereas the heat transfer coefficient is modified and includes the effects of both convection and radiation. I think these are a bit advanced topics and may not really be required for the discussions currently, but these are all for the concept so that we understand where we're going. Simultaneous heat transfer mechanism, as we discussed, that heat transfer is only by conduction in opaque solids, but by conduction and radiation in semi-transparent solids. A solid may involve conduction and radiation, but not convection. A solid may involve convection and radiation on its surface exposed to a fluid or other surfaces. Heat transfer by conduction and possibly by radiation is in a still fluid, and by convection or radiation in a flowing fluid. In the absence of radiation, heat transfer through a fluid is either by conduction or convection, depending on the presence of any bulk fluid motion. Convection is basically conduction plus the fluid motion. In that case, the heat transfer through a vacuum is by radiation. Most gases between two solid surfaces do not interfere with radiation. Liquids are usually strong absorbers of radiation. So these are the informations that are required to understand the simultaneous heat transfer mechanisms when we have conduction for solids, or we have radiation, convection, or conduction, both the modes, but dealing with gas. In vacuums, we generally have radiation only. So although there are three mechanisms of heat transfer, a medium may involve only two of them simultaneously. So this brings us to the next topic, which is the heat conduction equations. We have to understand that multidimensionality and time dependence of heat transfer. The conditions under which a heat transfer problem can be approximated as being one-dimensional. We have to try to obtain differential equations of heat conduction in various coordinate systems and simplify it for study of one-dimensional cases. Identify the thermal condition on surfaces and express them mathematically as boundary and initial conditions. Solve one-dimensional heat conduction problems and obtain the temperature distributions within a medium and the heat flux. Analyze one-dimensional heat conduction in solids that involve heat generation. Evaluate heat conduction in solids with temperature-dependent thermal conductivity. Although heat transfer and temperature are closely related, they're of the different nature. Temperature is scalar because it only has magnitude and doesn't have any direction. Heat transfer has a direction as well as magnitude. That's why it's a vector quantity. While dealing with coordinate system, we have to indicate directions with plus and minus signs because heat transfer, as mentioned, has a direction. The driving force for any form of heat transfer is the temperature difference. The larger the temperature difference, the larger the heat transfer. The prime coordinate systems, rectangular, cylindrical, and spherical, is something that we'll be dealing with. And it is expected that you already have some understanding from your vector courses about this coordinate systems and how to convert from one to another. Now the steady means no change with time at any point within the medium, whereas transient implies variation with time or time dependence. In special cases, variation with time but not with position, the temperature of the medium changes uniformly with time. Such heat transfer systems are called lumped systems. Heat transfer problems can also be multidimensional. And that is why the problems can be classified as one-dimensional, two-dimensional, or three-dimensional. In the most general case, heat transfer through a medium is three-dimensional. However, some problems can be classified as two or one-dimensional depending on the relative magnitude of the heat transfer rates in different directions and the level of accuracy desired. One-dimensional if the temperature in the medium varies in one direction only, and thus heat is transferred in one direction, and the variation of temperature and thus heat transfer in the other directions are negligible or zero. Two-dimensional, if the temperature in the medium, in some cases, varies mainly in two primary directions, and the variation of the temperature in the third direction and thus heat transfer in that direction is negligible. The rate of heat conduction through a medium in specific direction is expressed by Fourier's law of heat conduction for one-dimensional heat conduction as this. The heat is conducted in the direction of decreasing temperature, and thus the temperature gradient is negative when the heat is conducted in the positive x direction. Here, the temperature gradient dt by dx is simply the slope of the temperature curve, that is the Tx curve. The heat flux vector at a point P on a surface of a figure must be perpendicular to the surface, and it must point in the direction of the decreasing temperature. If n is the normal to the isothermal surface, and P, the rate of heat conduction at that point can be expressed by Fourier's law. For different coordinates like x, y, z, different axes, you can split it like this. A few examples for heat generation could be like electrical energy being converted to heat at a rate of I square R, fuel elements of nuclear reactor, isothermic chemical reactions. As we know, the heat generation is a volumetric phenomenon. The rate of heat generation unit is watt per meter square. The rate of heat generation in a medium may vary with time as well as position within the medium. Much of what we'll be understanding here, the mathematical parts, may not be always useful, but it's more for the advanced understanding about the mathematics of this topic. And we'll get into more specific course-related or your syllabus-oriented mathematical approach to these problems in future classes. One of that is the one-dimensional heat conduction equation. Consider heat conduction through a large plane wall, such as the wall of a house and the glass of a single pane window. The metal plate at the bottom of a pressuring iron, a cast iron steam pipe, cylindrical nuclear fuel element, electrical resistance wire, the wall of a spherical container or a spherical metal ball that is being punctured or temperatured. Heat conduction is these and many other geometries can be approximated as being one-dimensional since heat conduction through these geometries is dominant in one direction and negligible in other directions. We developed the one-dimensional heat conduction equation in rectangular, cylindrical, and spherical coordinates. This is something of our interest. So the heat conduction equation in a large plane wall To start with, we have to understand the rate of heat conduction in one, that is x direction, minus the rate of heat conduction as short distance delta x, plus the rate of heat generation inside the element is equal to the rate of change of the energy content of that element. So that basically leads us to some differential equations with variable conductivity and constant conductivity. In case of steady state, that equation actually comes down to a much more simpler option. For transient and no heat generation, steady state and no heat generation, it becomes much more easier. The simplification of one-dimensional heat conduction equation in a plane wall for the case of constant conductivity for the steady conduction with no heat generation is basically only d2t by dx2 equals to 0. When we are dealing with the same equation in a long cylinder, we have cylindrical coordinates and similar equation may be found. We can convert the same equation, or we can obtain the same equation for a sphere, for variable conductivity and constant conductivity. The typical parameters we can use it for is steady state, transient, with no heat generation, and steady state, no heat generations. We can actually make all this combine into one equation, which is a combined one-dimensional heat conduction equation. An example of one-dimensional transient heat conduction equation for the plane wall, cylindrical, and sphere reveals that all three equations can be expressed in a compact form, where n equals to 0 for plane wall, n equals 1 for a cylinder, n equals 2 for a sphere. In the case of a plane wall, it's necessary to replace the variable r by x. This equation can be simplified by steady state, for steady state, or no heat generation cases as described before. This brings us to general heat conduction equation. In the last section, we considered one-dimensional heat conduction and assumed heat conduction in other directions to be negligible. Most heat transfer problem encountered in practice can be approximated as being one-dimensional. And we mostly deal with such problems in the textbooks problems. However, this is not always the case. Sometimes we need to consider heat transfer in other directions as well. That is why we discussed about multidimensional heat transfer problems. And that becomes slightly tricky while we're dealing with rectangular, cylindrical, and spherical coordinate systems. With a similar approach, but this time we have to consider three-dimensional heat conduction through a rectangular volume element. And then the rate of heat conduction at X, Y, Z, or the rate of heat conduction within the element needs to be considered, which is equal to the rate of change of energy content within that element. And this brings us to this beautiful equation, which is the general heat conduction equation in rectangular coordinates in case of constant thermal conductivity. Where the property alpha is again the thermal diffusivity of the material. And this equation is known as Fourier-Biot equation. It reduces to these forms under specific conditions. At steady state, this brings us to the Poisson's equation. At transient, no heat generation is the diffusion equation. At steady state, no heat generation, it is the Laplace equation. The three-dimensional heat conduction equation reduced to the one-dimensional ones when the temperature variation in one dimension only. So we basically do away with the Y and Z axis. While dealing with cylindrical coordinates, we can simply use the relations between the coordinates at a point in rectangular and cylindrical coordinate systems. For spherical coordinates, we can also use the relations between the coordinates at a point in rectangular and spherical coordinate systems. What becomes more important after we have developed these equations is actually understanding the boundary and initial conditions, because that is how you're going to solve most of these equations in real life. The description of heat transfer problem in a medium is not complete without a full description of thermal conditions at a boundary surface of the medium. So basically, is the mathematical expressions of the thermal conditions at the boundaries are the boundary conditions. The temperature at any point on the wall at a specific time depends on the conditions of the geometry at the beginning of the heat conduction process. Such a condition, which is usually specified as T equals 0, is called initial condition, which is a mathematical expression for the temperature distribution of the medium initially. The boundary conditions could be following, which are like the specified temperature boundary conditions, where we actually deal with the temperature boundary conditions are defined already. Specified heat flux boundary conditions. The heat flux is more or less defined, and we already know the boundary conditions. Convection boundary conditions, radiation boundary conditions, the interface boundary conditions, which definitely deals with the interface of two or more surfaces. Generalized boundary conditions, which could be anything which is more generalized. Specified temperature boundary conditions. In terms, the temperature of an exposed surface can usually be measured directly and easily. Therefore, one of the easiest ways to specify The thermal condition on a surface is to specify the temperature. The one-dimensional heat transfer through a plane wall of thickness L, for example, the specified temperature boundary condition can be expressed at both the ends like T1 and T2, where T1 and T2 are the specified temperature at the surfaces at x equals 0 and x equal L, which is the boundaries of the surface that we're dealing with. Specified heat flux boundary condition. The heat flux in the positive x direction anywhere in the medium, including the boundary, can be expressed by this equation, which basically gives the heat flux in the positive x direction. For a plate of thickness L of flux of 50 watt per meter square into a medium both sides, for example, the specific heat flux boundary condition can be expressed like this. When we have a special case like insulated boundary, it can be modeled as a surface with a specific heat flux of 0. Then the boundary condition of the perfect insulated surface and x equal to 0, for example, can be expressed in a simple formula like this. On an insulated surface, the first derivative of temperature with respect to the space variable, the temperature gradient, in the radiation normal to the insulated surface is 0. We can have another special case, which is thermal symmetry. Some heat transfer problem possesses a thermal symmetry as a result of the symmetry in the imposed thermal conditions. For example, the two surfaces of the large hot plate of thickness L suspended vertically in air is subject to the same thermal conditions, and thus the temperature distribution in one half of the plate is the same as that in the other half. That is, the heat transfer problem in this plate possesses a thermal symmetry about the center, which is x equal to L by 2. Therefore, the center plane can be viewed as an insulated surface, and the thermal condition at this plane symmetry can be expressed in this form, which resembles the insulation or the zero heat flux boundary condition. The convection boundary conditions can be also expressed with some mathematical problems here, but may not be of our interest right this moment. The radiation boundary condition is rather more of our interest in this course. The radiation boundary conditions on a surface, basically the heat conduction at the surface in a selected direction is equal to the radiation exchange at the surface in the same direction. For one-dimensional heat transfer in the x direction in the plane of thickness L, the radiation boundary condition on both surfaces can be expressed with this form. This is something that we have discussed in the earlier part of this course, this lecture particularly. For interface boundary conditions, two bodies in contact needs to have the same temperature at the area of contact. An interface, which is a surface, cannot store any energy, and thus the heat flux on two sides of interface must be the same. The boundary condition at the interface of two bodies A and B in a perfect contact at x equals to x0 can be expressed in terms of these two equations. The generalized boundary condition for a surface may involve convection, radiation, and specified heat flux simultaneously. The boundary condition in such cases is again obtained from a surface energy balance, which is the heat transfer to the surface in all modes equal to the heat transfer from the surface in all modes. Once we have some understanding about the heat conduction equations, we understand the concept of boundaries, the boundary conditions, the various kind of boundary conditions. Now we are actually prepared for the solution of steady state one-dimensional heat conduction problems, which we'll cover in the next lecture and give a detail about how to formulate, look for general solutions, add in the boundary conditions, look for specific problems and solutions, some particular cylindrical and other kind of structures, heat generation, variable thermal conductivity, among others. Whereas for this course, this class, we covered the idea about steady versus transient heat transfer, multidimensional heat transfer, heat generation, one-dimensional heat conduction equations, heat conduction equation in large plane wall, heat conduction equation in long cylinder, heat conduction equation in a sphere, combined one-dimensional heat conduction equations, general heat conduction equation for rectangular, cylindrical, and spherical coordinates, the boundary conditions and initial conditions. And further, we'll get into solutions of steady one-dimensional heat conduction problems and heat generation in solids, variable thermal conductivity in the next class.